lecture 23 in the series of acoustic materials and metamaterials. I am Dr. Sneha Singh of Mechanical Industrial Engineering Department at IIT Roorkee. So in this lecture we will continue our discussion on microperforated panels and will conclude. So in the last class we studied that there are certain limitations with single leaf MPP absorbers, that they are not able to provide absorption wide range, and so that was one of the major limitation, that they are not able to provide the absorption wide range, and then certain modifications are then done to the single leaf to try to eliminate this limitation. So in the last class we studied about one such modification, that was what happens when a porous material is filled inside such MPP, and we found is that provided we choose the total resistance due to this porous material correctly, and it does not become a hard blocking material and it can allow sufficient air to pass through. So in that case the porous material will end up increasing the absorption magnitude and broadening the absorption peaks. In this class we will study about another two modifications, which is if we have double leaf MPP and if we have the MPP with a partition cavity, and then we will see what are the applications of MPP in various industries. So what is a double MPP absorber? So till now we have studied that we had a single microperforated panel which was having an enclosed cavity behind and then a rigid wall backing. So what if we have two such layers of microperforated panel? So in that case, so this is the double leaf MPP absorber. So a simple construction is where you have an MPP1 and MPP2. So one of the limitations with single leaf is that first of all it is not able to provide a wide range absorption, and the second one was that it always needs to have a air cavity backed by a rigid wall. So there is a requirement for a rigid wall at all the times for an MPP to work. So single leaf requires first of all wide range absorption is not possible, is difficult rather to say, for a single leaf, and the other limitation was that it requires a rigid backing. So this design constraint is always there, and because it always requires a rigid backing, so this limits our options to place and apply the MPPs in various portions. So we can only apply it on the walls or near the walls. We cannot apply it midway or inside some complicated machinery component, because every time we have to only apply it near a rigid backing. So these were the two limitations. So this double leaf MPP tries to overcome both these limitations, especially this requirement for a rigid backing. So this is a basic construction of this double leaf MPP. What we have two MPP layers, and the distance between them here I am representing with the variable d, and usually in most of the cases these MPP layers they have different hole radius, because we know that as hole radius and porosity changes, then the absorption characteristics also change. So it's better to have two layers one by one with different hole radius and porosity, so that we can get two different absorption peaks and we can have a more broader absorption. So that is why these parameters, so when MPP1 and MPP2 was chosen, the thickness is of the first one I am representing by T1, and for the second one I am representing by T2, and similarly hole radius by R1 and R2, and we can simply represent the porosity by 1 as sigma 1 and porosity of the 2 by sigma 2. So the control parameters are varied for both the MPP layers and they are maintained at a particular distance, and here the air cavity is actually the air inside, the air between both these MPPs. So here a rigid backing is not required, it may be used. So when we will later study, we will see a few graphs where rigid backing is also added, and then without the rigid backing also we can use this kind of MPP. So now here in this particular construction there is no rigid backing. So when there is no rigid backing, which means that some transmission will take place. The rigid backing was ensuring that the sound is getting absorbed, but from the other end the transmission is not happening because the sounds are getting reflected from the rigid backing. So it was sort of blocking the transmission of sound from the other end of the material. But in this MPP, because now we do not have a rigid wall, so some transmission will take place from the other end. So some sound wave will be absorbed, but some transmission will take place through this backing. So if we represent the sound absorption coefficient by alpha and this transmission intensity coefficient, or the intensity or the fraction of intensity that is getting transmitted from the other end of the absorber, as tau, then a better way of measuring the performance of such MPP is using alpha minus tau, because what is the purpose of this MPP? To reduce the overall noise both before the material as well as after the material. So let us say that this was a layer and some intensity of 1 was incident on it, and so only an intensity of 0.3 got reflected. So overall alpha becomes 0.7. So 30% of the wave got reflected in this end, but 0.2 of it got transmitted from the other end, 0.2 of the original intensity. So 30% of reflection and 20% of transmission. So overall loss is what? The overall loss is going to be 1 minus 0.3 plus minus 0.2. So if 1 is equal to the original intensity, and 0.3 is the fraction of intensity which is reflected, and 0.2 is the fraction of intensity that is transmitted from other end, from the back end. So in that case, the total loss that is happening, the total loss by this MPP material is not 0.7, because 0.7 would have been the loss if nothing came out of it. So the total loss effectively is going to be 1 minus 0.3 minus 0.2, which over here becomes 0.5. So 30% of the energy is reflected, 20% is transmitted, and the remaining 50% of it within the material is dissipated. So this is the fraction of incident intensity that is dissipated by the MPP. So this is the energy that the MPP is controlling. So a better way of measuring the performance of this MPP could be alpha minus tau. Here this is what, by definition this is alpha, because it is 1 minus the intensity reflection coefficient, so 1 minus r square, and this is tau. So alpha minus tau will give you, this gives you what? It is the fraction. So this gives us the fraction of the incident intensity that is lost or dissipated while passing through the double leaf MPP. So this becomes a better measure. So before we were studying the plot of alpha versus frequency and to study what is the absorption by the MPP. Now we will study the plots of alpha minus tau versus frequency to see what is the effective absorption by the MPP. So we are removing the transmission part. So now here if we look at this figure again, Then if there was no first material, so first material, the second layer was not there, we just had a one microperforated panel followed by a rigid backing, then it would be represented by the first circuit here, only this first loop here. So where we had, it could be represented by, this is the impedance of the incident medium, this is the impedance of the incident medium, this is the impedance by the MPP panel, and this is the impedance by the air cavity backing, air cavity. So the Z of MPP and the Z of air cavity, they are in series, and that is why the total acoustic impedance that we derived for single leaf was Z of MPP plus Z of cavity. So this is the original circuit. So we can represent this MPP connection as an electrical circuit, and this is how we can represent it. So when a second layer is added at a distance d, then what it does is that now this layer is acting as a parallel layer to this air cavity. So both MPP1 and MPP2, they have a common air cavity in between, and they are acting in parallel. So the equivalent air circuit, the electrical circuit is like this. Here this is the impedance of the MPP2, and this is again the incident rho c due to the incident wave, and this is the common air cavity in between. So if you solve this circuit, so we already know we have a model by that was proposed by Professor Dayuma, and in that model the total Z of an MPP was given to you. So you know the R1 value, which is the real part of the Z, and the imaginary part of the Z. So these values can be found from the model proposed by Professor Dayuma, which I had discussed in the very first lecture on MPP. So here now, if you, in this particular circuit, if you solve for the total impedance, what you get is this in series with the parallel of this. So these are in parallel, so they are solved together, and then whatever equivalent resistance we get from this resistance in parallel, we add them together to this in series. So the first resistance plus this is going to be, now these two resistance are in series, so the total becomes rho c again, because we are representing everything in the relative terms. So Z of MPP we represent it as a relative Z with respect to the incident medium. So Z by rho c is what we are representing. So rho c, the relative impedance then becomes 1. So this we can take as 1, and this will be the impedance relative to this rho c. So this will be R minus, this will be R plus 1. So these two are in series, so they are added together. So R plus 1 and will be the real part, and this will be the imaginary part. So R2 plus 1, and then this is the imaginary part. So this is the total resistance in this particular circuit, in this particular loop, and this is in parallel with the Z of cavity. So 1 by ZC, and this equivalent is what is then added in series to this. So this gives us the, so you can represent this double leaf as a electrical circuit, and then you can solve for the total Z, and then you know the individual parts R1 and M1. So by the model, I had already given you an equation for this in the first lecture. So R of 1/2 can be represented as 8 mu t 1 or 2 divided by sigma rho c r under root of 1 plus x square by 32 plus under root of 2 by 16 r by t. If you add end correction, then 16 becomes 4. So two formulae were given to you in the very first lecture on MPP. So using that formula, you can find out what is the real part of the impedance of MPP and the imaginary part of the impedance of the MPP. So this is known to us individually based on the various design parameters, and then we can solve this to get the total of the circuit or the total due to this double leaf MPP. And when you find the total Z, so usually these things are not done like hand calculations. We have computers were writing the algorithms, and then numerical study is performed. So all these value is fed into a computation tool. It does the computation and then it sees how the alpha varies with the various design control parameters. So once the total Z is calculated, alpha can be obtained by this equation, because alpha is given by 1 minus Z minus 1 by Z plus 1 whole square, where Z is equal to some real part of Z plus J times the imaginary part of Z. So Z can be represented by its corresponding real part and imaginary part, and this is the overall function. When you solve it, this is the equation you get. And if you want to go more into details of this equation, you can also refer to the lecture on sound medium at the sound propagation at medium boundaries, where we derived that the R for a medium is given by Z2 minus Z1 divided by Z2 plus Z1, and 1 minus R square then was found, and it was represented by this form of equation. Tau was also found. In the same lecture you will find the equation for tau. So both derivations are given to you when you study the lecture on sound propagation on medium boundaries. So where you can solve for the Z total and you can find out what is alpha, what is t, and then you can plot alpha minus tau. So you can plot this quantity alpha minus tau, which will give you what is the total performance as a function of frequency. Okay, so this is when we consider that both the thin panels, now we do not have any rigid backing and they do not have any strong support. So sometimes the panel, when the sound is incident on the panel, it can also cause the panel to vibrate along with the air. So this is when the panel is not vibrating, so there is no leaf vibration or no panel vibration. But there can be a case when the panel itself can start vibrating as a sound wave is incident on it. So in that case, overall the leaf vibration has an effect that it adds an additional impedance, but it adds an additional reactance part which is directly proportional to the mass of the panel. So here this is the original impedance, and because this leaf is vibrating, so an additional reactance part which is omega into m times, where m1 is the mass of the first panel. So this reactance is added in parallel. Similarly, if this leaf is vibrating, then this is the original impedance and another reactance is added in parallel to account for. So all of this accounts for the leaf vibration. So if the individual leaves are vibrating, then an additional reactance is added to it. So if only one leaf was vibrating, then we will only take this one. So let's say only first panel was vibrating, the second one was not vibrating, then this part will be removed and only this impedance will be taken. This part will not be taken, it will be removed like this if only one leaf was vibrating. So whenever leaf vibration is added, then a reactance is added in parallel which is directly proportional to omega times the mass of the panel. So this becomes our new circuit. When you solve it, you get another complicated expression. So first of all, you find out what is the equivalent of this. These two are in parallel. What is the equivalent of this? And then this is added in series with this. And then these together are in parallel with this. And the equivalent of the entire thing then is added to this equivalent to get the total Z. So solving this particular circuit, this is the end result. I am directly giving you the end result. So here this part is okay. So this part is this particular impedance. So it is the equivalent of these two being in parallel. This is this first part, and then this is ZC. So 1 by ZC plus 1 by the equivalent of this, and whole inverse will give you the equivalent of this entire circuit. So this part, so just like this part was the equivalent of this full block, this part is the equivalent of this block. So this part is the equivalent of this block, and then rho c is taken as 1 because we are finding out the relative impedance. So, this part is then added to 1 to get the entire equivalent, the entire impedance of this whole circuit, and then these are in parallel. So, the overall parallel thing is added to the previous one. So, it is a, this is the expression we get for Z total. R and M for both of the real part and the imaginary part for the impedance of an MPP again from the same model is already given to us. It is this expression. Alpha and tau can be found. So, all of these calculations, if you are taking this course, I will not be asking you to do all these calculations because these are series of complicated calculations. This is just for the understanding that what does a double leaf or what is the effect of an additional leaf behind. So, an additional leaf means that one impedance is now being added in parallel with a common ZC. So, that is the overall effect, and it is just to show you how such numerical computations are done. So, computation tools are available and all these complicated computations are done. So, when you get alpha and tau, so you have found alpha and tau when there is no leaf vibration, you have also found alpha and tau when there is leaf vibration. Then you can plot alpha and tau. So, alpha and tau can be plotted with respect to frequency. So, let us directly give you what is the effect of adding this double leaf. So, this graph shows the alpha minus tau of a single leaf. So, this is the net absorption by a single leaf, effective absorption. When another leaf is added to it, so usually the absorption peak, it decreases a little bit, but overall the absorption at the low frequency is enhanced throughout. So, throughout from the very beginning till the resonance condition, the absorption magnitude is enhanced in this low frequency region, and then it follows the same pattern. So, that is the effect of double leaf, that suddenly low frequency absorption is enhanced throughout. And if we add a rigid backing at the end, so if we have double leaves plus a rigid backing, then in that case what it does is that it improves the low frequency absorption and broadens the peak, but it is not done throughout. So, I will write down the effect here. So, I can write down here also. So, when only double leaf enhances low frequency absorption throughout, which means throughout all the low frequencies, but the maximum absorption may reduce a little, not much effect, but a little reduction. And when the same double leaf is backed by a rigid wall, so what happens is that now the absorption peak is enhanced. So, absorption magnitude increases throughout. So, the shape remains the same, alpha minus tau versus f shape or profile remains same, only there is an overall increment throughout. So, it just get a bigger peak, it will not be a constant absorption. So, there will not be a broadband low frequency absorption, you will still get a peak, but the peak will be broadened and it will be, so it will be a slightly wider peak with an increased magnitude. So, that will be the effect of double leaf by a rigid wall. So, I am restating these results here. So, here the double leaf MPP, it significantly enhances the absorption at low frequencies, broadband, let us say broadband low frequencies because it is happening throughout, and so it can enhance it at all these broadband low frequencies where the single leaf MPP is not efficient. and it provides almost similar absorption characteristics at the resonance and higher peaks, although it is slightly reduced, but it is within the limits. Okay. Now, the absorption mechanism of a double leaf MPP can then be interpreted as it is both a resonator. So, at middle to high frequencies it acts as a resonator, and at low frequencies it is acting as a acoustic flow resistance. So, at the middle to high frequencies you see it takes the same form as a resonator. So, you get some peaks at certain frequencies, but at low frequencies there is a broadband absorption. So, there is no peaks, sharp peaks observed, but there is a constant absorption throughout at the low peaks. So, at the low frequencies, so there is a constant absorption at low frequencies. So, you can assume that at low frequencies this particular double leaf MPP, it is acting like a typical acoustic resistance which is independent of frequency. So, you are getting a constant value here, and then suddenly middle to high frequency it behaves the same way as single leaf MPP or as a resonator. So, for best performance what you can do is that you can set the control parameters so that the surface resistance becomes rho c at the resonance condition. So, when the surface impedance of the double leaf MPP is rho c and the incident medium surface impedance is also rho c. So, when there is an impedance match, then there will be a perfect absorption, alpha will be equal to 1. We know that alpha is equal to 1 minus Z2 minus Z1 by Z2 plus Z1 whole square. So, when Z1 equals to Z2 equals to rho c, so in that case alpha becomes equals to 1. So, this is one way of attaining maximum absorption, that is you can equal the surface impedance to that of the incident medium at the resonance frequency. Then some other things that can be done is that we can have at lower frequencies lighter leaves can be, if the leaves are lighter they will cause more significant drop in absorptivity, because here the vibration of the leaf will cause a decrease in the acoustic flow resistance. So, in the low frequencies the absorption is mainly due to the resistance to the flow of air, and if lighter leaves are used then they are vibrating along with the air. So, there is no the resistance to airflow is decreased. But at resonance frequencies the opposite happens, the lighter leaves they can cause more increase in the absorptivity, because at higher frequencies, at resonant frequency the absorption is because of the vibration. So, absorption is because now the sound energy is doing work to vibrate the air and the panel. So, when the lighter leaves are used, panel will vibrate, there will be stronger resonance and more energy will be lost. So, this is the opposite effect at low and the high frequencies. So, the application of this kind of double leaf MPP then becomes that now just like an MPP, now there is no restriction that it has to be applied only where you have a rigid backing. So, they can be used as space absorbers. They can be installed anywhere in midway when there is no rigid backing, or even in the open air conditions. So, there need not be an indoor application or an application near a rigid wall backing. They can be used anywhere in this space as a screen or a partition, and they can also be used in some complicated areas where backing is not available, such as the different parts of machinery and buildings. Okay, so the last form of modification that is usually studied, that has successfully been able to successfully eliminate the limitation, is when the cavity that is behind a single leaf MPP is partitioned or sectioned. So, one of the common practices we use a honeycomb structure. So, this shows a typical cavity partitioning. So, we can have a micro perforated panel on the top of it, and behind we have again the air cavity, but now this air cavity is divided into segments or partitions, and the common one being a honeycomb kind of a structure for dividing the air cavity. So, this shows the effect. So, here the source for every data is given to you. So, here this is an experiment carried out by Liu and Herin in 2010, and they found that when the cavity is partitioned using a honeycomb structure, then suddenly this is the performance, this is the insertion loss due to original MPP, and this is the insertion loss due to the MPP with the partitioning, and overall the insertion loss has increased by 3.2 decibels. So, they are able to reduce the noise more by 3.2 decibels. So, as you can see, throughout the alpha has been enhanced for such an MPP. So, performance increases. So, how is this explained? So, when we have the sound, when we have the air cavity backing, then different modes can be set up within this air cavity to represent the sound wave propagation. So, we have this air cavity becomes a constraint medium. At one end we have a driving source and at the other end we have a rigid backing, and within this constraint medium it will have certain modes, and the modes can be represented by, so if it is, this is the three directions for sound wave propagation here, L, M and N. So, here you can see L is the normal direction, this is the normal direction or the direction that is normal to the panel, and these are all transverse directions. Transverse directions. So, in that case the total frequency can be represented as a combination of the frequencies at the three different directions, the natural frequencies at the three different directions. So, we can represent the various modes by three indices, which is L, M and N. So, 100 means that L is equal to 1, M is equal to 0 and N is equal to 0. So, this means that the transverse frequencies are 0, only the normal frequency is getting its first value. So, which will mean it is the first pure normal mode. Similarly, if we have 0 1 0, which means that M is equal to 1 and L and M are 0. So, this is the value of L, M, N. So, when these two are 0, which means that normal mode has not set up, this is not set up, only the total mode is only due to the transverse mode. So, this is the first pure transverse mode in the M direction. And similarly, if we have some expression like 1 to 1, so this is a way to represent the various modes set up within a cavity. So, 1 to 1 means that the first mode in the normal direction, the second mode in the M direction and the first mode in the N direction. L is equal to 1, M is equal to 2 and N is equal to 1. So, this is a combined mode due to this first normal mode, second M mode and first N mode. So, just to give you a notation, because I will show you a graph where these notation is used. So, the same scientists, the same researchers Liu and Herin, they wanted to find out what is the reason why partitioning a cavity is improving the performance. So, they in the same graph they measured that the various peaks they correspond to these individual modes, and what you see is that when the cavity is not partitioned or the cavity is kept the same, then all the transverse modes like this one, and then you can take the example of this one. So, whenever you are getting a transverse mode, a pure transverse mode, let us say even here. So, whenever you are getting a pure transverse mode where L is equal to 0, the first indices become 0. So, in that case the magnitude is diminished, only in the normal modes the magnitude is enhanced. So, the observation was that if no partitioning is done, then the transverse modes they are diminished, and when a partitioning is done, then it suddenly enhances the transverse modes as well. So, this is the result. It shows that partitioning of the adjoining air cavity, it increases the overall sound attenuation due to the MPP by approximately 4 decibels compared to when air cavity is not partitioned, and the reason was that from the measurements it can be shown that the sound attenuation at oblique incidence is enhanced and sound attenuation is almost unaffected at normal incidence. So, when the cavity is partitioned, now the sound waves they have more directions to propagate rather than just the normal direction. So, they are also propagating along the transverse direction and the normal direction, and these different modes are set up. And so studies on the effect of a cavity on the acoustic moods inside a closed cavity shows that MPP was effective at damping the acoustic cavity modes normal to the MPP, but ineffective at damping the modes that are tangential to the MPP. So what it means is that the insertion loss is remaining unchanged at transverse, is very less at transverse modes. The insertion loss was higher at the normal modes. So this is what was observed, that IL is higher for the original case, IL is higher at the normal mode, but at the transverse direction it is almost low or 0. So partitioning the cavity, it is sort of imposing a condition that the waves can only travel along the normal direction. So now both the sound wave propagation along the normal direction is getting reduced, or the losses are taking place both at the sound wave along the normal direction, and the losses are also taking place when the sound wave is propagating along the transverse direction. So now even the transverse direction propagation is getting diminished, or losses are taking place. So that is what the partitioning is doing, and overall the performance is increasing. So you can say that the partition cavity is providing some sort of motion constraint condition. So the transverse mood is diminished. So along the normal mood, the losses are due to the resonance phenomena, but along the transverse mood now the losses are due to the motion constraint that is imposed by the cavity. So overall all these moods are diminished. So we studied about these two particular sort of modifications we do to single leaf MPP, and they are applied widely over automotive industries, even in aerospace. So you can see that the lining material that is used in an aeroplane cabin, for example in the Air India Dreamliner, in the new series of it, you can see it has very small micro perforated holes. So that is acting as a micro perforated panel. Similarly, the same kind of panels can be installed in the buildings as well. So it has numerous applications in various industries, and it is one of the newest materials that we have been studying. So thank you for this lecture, and in the next lecture we will start with our discussion on metamaterials. Thank you.